50 years ago, Professor Phil Anderson wrote a paper, Absence of Diffusion in certain systems that are nowadays known as the Anderson model. I'm Martin Zirnbauer, and together with Jan Fjodorov, Ilya Gottschalk, and Tom Spencer, I'm organizing a 6-month program devoted to this phenomenon of Anderson localization, understanding it, and the ramification it has taken in physics and mathematics since its introduction 50 years ago. The program is being kicked off by a 2-week training course. We're having a number of graduate students, postdocs, and young researchers in town following the lectures. Isn't it fortuitous that halfway through the training course, we now have the pleasure of hearing Phil Anderson's reminiscences of this event? I wouldn't have thought of bringing him here, and if I had, I probably wouldn't have dared to invite him. It was the initiative of David Wallace, who sent email to Phil. He somehow knew that Phil, for the past 4 or 5 days, was in the south of France attending a conference on supersolids. And Phil agreed to come here and be with us for a few days and deliver this lecture. I learned today that this is a kind of homecoming for him. He was in Cambridge for 8 years, from 1957 to 1965, being chair of the Cavendish Lab. Nope, chair of the condensed matter theory group in the Cavendish. That's correct now, right? Okay, enough of this. Please, Phil, take the stage.
Churchill College is also slightly familiar territory to me, since in 1961 I was the second visiting fellow in physics that the college ever had. It's a great pleasure to be here, again, partly because it's familiar territory, and I still have a considerable number of good friends in Cambridge, partly because it's the Newton Institute, and who can not be pleased to be speaking in the Newton Institute. There isn't any bigger name. I've lectured in somewhat daunting places. I've been lectured in front of, given a beta lecture in front of Hans Bethe, and lectured in the lecture room that Pauli used to lecture in. But the Newton is just a bigger name than all of those. Anyhow, it's a pleasure to be here and to tell you about how localization came to be. Partly, it became to be because of the extraordinary extraordinary atmosphere of the Bell Laboratories in its 30 or 40 great years, from the late 30s to not too long ago, 1984 is one important date when it was broken up by order of the U.S. government. But in 1956, we happened to have decided that those of us who were theoretical physicists needed a little company, and so we formed a theoretical physics department and asked demanded of our management that we have certain privileges. We didn't know that they were likely to give them to us, but they did indeed. And in very wisely, because they had been losing theoretical physicists about 1 or 2 a year for the past few years, and they'd lost Bardeen, and they'd lost Wanier, and they'd lost, they were about to lose Hal Lewis, and various others. And so they decided, well, maybe these theoretical physicists were a strange lot, and they wanted some things, but they were also very useful. So perhaps they'd give them these things. I don't know who made the decision, possibly W.O. Baker, who was for a long time president of the labs at that time. He was research vice president. And among the privileges they gave us was to have visiting summers. We could ask almost anyone we wanted to come and visit us in the summer. The first summer of our new department was 1956, and this lasted for about 3 years, and then it tailed off, mostly because other people got the same idea, and we didn't have a completely open field anymore. But at the time, we could ask almost any theoretical physicist, especially those in condensed matter, we wanted, and they were likely to come. I've given you a few names here just because these are rather surprising names. Bruckner is famous for his work on nuclear matter. Montreux on statistical mechanics. John Ward is the unhonored member of the group that invented the electroweak theory. Gregor Wenzel was a massive figure in quantum field theory, but there were many others. And we happened to have a young man from Illinois, actually, as a summer student. That was Bob Schrieffer. But he was not one of the eminent foreigners we invited. We were also allowed to invite summer students from various places. As a result, partly of this wonderful atmosphere, condensed matter theory was exploding in all directions. There were two of the people that I mentioned here, Montreux and Ward, were one of 3 simultaneous inventors of the formalism of the temperature-dependent diagram theory that is nowadays associated with Abrikosov, Gorkov, and Jalashinsky, for instance. But one of the areas that was burgeoning at that time was transport theory, quantum transport theory. Of course, we were interested in transport theory because our masters were very interested in transport theory. They were worried about semiconductors for some reason. One approach that was just developing at that time was a generalization of wartime developments called multiple scattering, of which Lax and Bruckner were some of the originators. From a later point of view, I've often called it sweeping dirt under the rug. The idea being that instead of studying if you wanted to study the properties of an impure material, you replaced it by the closest approximation to a pure material. You tried to make it as similar as possible to a pure material, gave a k as the wave number as a small imaginary part or something like that, and tried as best you could to make it into the equivalent material. There was the classic Boltzmann approach, of which there is a massive paper in PhysRev of 1957 by Kohn and Luttinger, As I say here, it had 50 pages and 10 appendices. It was a bit heavy breathing, but I'm not by any means pouring contempt on it. One of its results, the Luttinger theory of the anomalous Hall effect, you don't need to know what that is, was only recently confirmed in 2004 or something like that. Confirmed finally and without any shadow of a doubt by one of my colleagues, Puanong, at Princeton. And it's an interesting and rather revolutionary concept that they used. But it was a bit heavy breathing at 50 pages and 10 appendices. It was the last Boltzmann treatment of quantum transport, perhaps, or nearly the last, because we would do one of the things Lax was doing, but Yogo Kubo in Kyoto was doing it somewhat better, was the Kubo formula, the so-called Kubo formula for the conductivity. But also, kind of quietly simmering under the surface, there was another small group worrying about other things. What we were doing was what I was doing with my friends Elihu Abrahams and David Pines, was named by Larry Walker, who has a sharp wit. He called it cisport theory. We weren't doing transport theory, we were doing cisport theory. Why were we doing this very strange and much simpler and fortunately much briefer piece of work? Was that we were motivated by certain experiments that were going on at the same time, and that I was more or less in charge of the interpretation of, being carried on by George Fayer and his co-workers, that he called Endor. George called it Endor after the Witch of Endor, and he was quite appropriate. He was an Israeli and had fought in the War of Independence in 1948. He's a very tough guy, as a matter of fact. Never play poker against him. And I'll show you what he was doing, and although I've had to take the slides from his 1958 or thereabouts paper, so they're kind of in, where did this, there it is. I have a pointer here. This is a schematic picture of, there's a dot, of a phosphorus 31 atom on a silicon lattice. I've drawn it as a square lattice because you can't draw a diamond lattice on a two-dimensional sheet. You put into silicon a few phosphorus 31 atoms. These phosphorus 31 atoms have an extra plus charge, and therefore they attract, and they are so-called donors. They have an extra electron, which has a very big fat wave function. I don't know. Yeah, there it is. This fat wave function is an electron which is spread out over quite a few of these silicons. The phosphorus 31 has a spin, and so the line, and what you do is to study magnetic resonance of that electron on the phosphorus 31. Among the silicon 28 atoms, which have no nuclear spin, there are a few silicon 29s, about 5%, in natural silicon. And these also, since it's an odd isotope, have little spins of 1/2 on them, and they also interact magnetically with the electron. As a result of this combination, when you sweep the magnetic field and study the microwave signal that you get a split line split by the phosphorus magnetic interaction with the silicon. It's a simple S.S interaction. And so you see one line with the phosphorus spin parallel and one line with an antiparallel at a really low density. But these lines are not infinitely narrow. They're rather broad. But it turns out that the breadth of the lines is almost entirely due to the silicon 29s. Each phosphorus has a set of silicon 29 neighbors randomly distributed, and this random set of silicon 29 neighbors also has spin up, spin down. And so you can investigate that line and you find that it's not a single line, it's thousands, well, billions of individual lines, so-called spin packets, each of which is remarkably narrow and which corresponds to a particular phosphorus ion, a particular atmosphere of silicon impurities or silicon neighbors. If you increase the number of phosphorus you have, you find that things look very similar, except you begin to see a little hump in the center and little humps on each side of it. What are those? Those are phosphorus groups of phosphorus ions in which there is some motion either of spin or of charge back and forth between three phosphoruses close together or two phosphoruses close together. Two phosphoruses close together would have 1, 2, 3 lines. Three phosphoruses close together would have 1, 2, 3, 4 lines. Just because of they would be averaging over the net, over the different phosphorus ions in contact with them. As you go to more phosphorus ions than that, some odd things begin to happen. The lines turn over. It's a complicated business. These intermediate lines become even more prominent. And then when you get to quite a high density of phosphorus, 3 times 10 to the 18th per cc, suddenly the line flips over and becomes very, very narrow, narrower than any of these. And that means that the electrons on the phosphoruses are sampling the entire distribution of phosphorus environments, and therefore they are doing what is called exchange narrowing or motional narrowing. They're averaging out all of that hyperfine structure, and one may assume the electrons on the phosphoruses are more or less free. So George was seeing this fascinating evolution of his spectra, but being a clever fellow, he invented a method of really studying it, and I won't go into as much detail about that. What he does is to, in the first place, take this sample. It's possible for him to stick to that particular magnetic field and apply a lot of microwave energy. And what happens is that rather than saturating the whole line, he saturates only a narrow little slice of it, and he does what is called digging a hole in the line. Then he puts an extra coil around his sample chamber, a little wire coil, and he applies radio frequency, 1,000 times lower frequencies, low frequencies that affect the silicon ions, the silicon 29s, and the phosphorus ions. And the result is, well, it's a mess because he always insisted on taking his figures strictly from the real data. But this frequency that he applies, I can't, this pointer just doesn't point. Anyhow, this frequency that he applies affects this hole that is dug in the line, and it affects it at this entire spectrum of, this is the deepest hole in it. This is where the average phosphorus hyperfine structure frequency is, but there are literally millions of little squiggles, and in fact we could roughly identify those squiggles with particular silicon 29s that were a particular distance from the original phosphorus. What this is telling you is that each silicon 29 is retaining its own frequency, and that the electron is staying on its own ion and looking at that particular silicon 29, and only when we come in with an external frequency does that silicon 29 spin change. And then taking that graph takes minutes, seconds, minutes. It doesn't seem to care much. So the frequencies of those lines weren't changing, although, well, we looked up what had been done previously. The existing theory is that the spins in a solid sample diffuse. And also it's that the electrons in the solid sample should diffuse. You couldn't exactly set the concentration so that there was exactly one electron per phosphorus. It was unthinkable, in fact, and indeed this didn't depend seriously on whether you did or not. But, or there's the concept of the impurity band. The phosphorus electrons are supposed to move around at will in a so-called impurity band, and we, as theorists, had assumed that, I think it was Bardeen's concept first, it may not have been, that this concept of there being a band of energies for these phosphorus impurities was correct. And wherever we looked in the literature, we found that the assumption was that there would be a diffusive motion at the very least, if not a metallic motion, and that this diffusive motion would follow the conventional golden rule. There'd be a density of states, some kind of hopping integral, either an exchange integral or an electron hopping integral. In every case, apparently, at a low concentration, all the spins are local. The electrons, the spins of the electrons, the spins of the phosphorus nuclei, the spins of the electrons themselves, physically, the phosphorus nuclear spins, the silicon and the silicon nuclei. There was no nuclear spin diffusion, no electron diffusion. Working with me, I had L.U. Abrahams and David Pines, and L.U. particularly worked very hard to estimate these diffusion integrals, or hopping integrals, the various J's and T's, hopping integrals, and he really convinced us that this concept of diffusion of these electrons or the spins failed by many orders of magnitude at low concentration, many orders of magnitude in several cases. I'm going back to my earlier notes, or next one. Oh, I guess it is still on this paper. I didn't think of this as a new idea, but in fact, it's been one which I've observed works very, very well. If you really want to find a new mathematical result, something really new in mathematics, study experiments. Don't go on studying, working with your pencil and paper. Look at nature. Nature has all kinds of new mathematical ideas, and you're unlikely to be as clever as nature. And so it's what, if I've ever invented anything really new, it's usually been because I was fixated on the experiment and determined that I would figure out how those experimental anomalies arose, and this was one of the first of them. There's a good description of the situation before the localization paper that's in a rather surprising place. It's this reference, Canadian Journal of Physics, 34-13-67 in 1956. If you ever read any literature about the Mott transition, you'll find that that is the same reference, except the 67 is wrong. It's about 10 pages earlier. This is a discussion remark by David Pines after he happened to be at the same Canadian meeting where Mott wrote his second important paper on the Mott transition. And he stood up after that paper, and either he stood up or anyhow, he was quite careful to write out in some detail the dilemma that we were in. And as I say here, David discusses the fact that we were very puzzled, but he properly does not mention my still speculative thoughts on localization. And if you want my opinion, the reason he didn't mention them was that he didn't believe them. So why do the frequencies remain stable for minutes if the electrons are hopping around according to the golden rule? Well, obviously the electrons aren't hopping around according to the golden rule. Well, at that time, I was still fairly close to my old friend Tom Lehrer, who'd written a number, the entertainer, who'd written a number of songs. He's also a mathematician. And the advice in one of these songs, which is the song called Lobachevsky, goes more or less like this. I'm not going to sing it, don't worry. But he says, what am I going to do? Plagiarize, plagiarize, plagiarize. Don't let no one else's work evade your eyes. Don't shade your eyes, plagiarize, plagiarize, plagiarize. Only remember, please, always to call it research. Well, that's what I did. I didn't actually know much about diagrams at that time and self-energy sums, so I read a lot of Dyson particularly, and was helped through it by my colleague Peter Wolf, who was one of the theory group. I had to turn the idea of diagrams backward to use what Feynman called a propagator, but I decided I would call it a or I would use a locator, and a starting energy that was local. I learned a lot about the statistics of non-repeating paths from Hammersley, who was just writing, the mathematician Hammersley, who was just writing about percolation. And why did I know about percolation at this early stage? Because Conyers Herring, another of my colleagues in the theory group, reads everything. The idea of critical concentration is there in Hammerly's writings. I had to do some sums on singular distributions, and I plagiarized those from my own work on line broadening, which had been in my thesis. But that goes back to the Russian school, Kolmogorov and Markov and people like that. So I produced a proof that there exists a localized regime. It's not a proof, of course, not such as the mathematicians in the room would accept, but it was a proof to my satisfaction. I took care of the problem of local pairs with two close energies by introducing the idea of self-energies. But of course, the reason I didn't really worry about the mathematics of the proof was that this was by no means an accurate physical representation of the system that I was looking at. The system I solved was strictly linear, but the experimental systems all had interactions. In particular, one thing that worried me very much was that it had the strong interactions that Mott was talking about, and I wondered if some of the localization effect wasn't due to Mott's interaction idea rather than to my randomness idea. But the great advantage of experiment was, well, at least there weren't strong interactions in the magnetic degrees of freedom and the spin diffusion degrees of freedom. And the other thing is that there was this experiment, and the experiment told me that there really was no motion at low enough temperatures in this system. So I never had I'm sorry, down here there's moment stout. Now we hesitate for a 20-year interlude, which time the great majority of theoretical physicists who didn't believe it had to were convinced mostly by Neville Mott. And it's been, in my experience, young theoretical physicists are much more conservative than old theoretical physicists. It isn't the old fogies you have to convince, it's the young fogies. But the young fogies did gradually begin to be convinced. Mott was, during this time, tying the idea of localization to conductivity theory. I was just talking about diffusion, and he was interested in a measurable quantity, although in principle you can connect conductivity to diffusion by by the Einstein idea. He noted that Joffe Regel in 1960 had already said that the mean free path L less than the wavelength was an impossibility. And so in 61, he introduced the idea of a minimum metallic conductivity. Actually, that minimum metallic conductivity, although no one found this reference until quite a bit later, had been observed many years before, in 1914, during the First World War, by W.F.G. Swan on bismuth films. He observed the two-dimensional equivalent. He found that his bismuth films stopped being metals at the minimum metallic, Mott's minimum metallic conductance. Mott noted that this involved the quantum unit of conductance, which is nowadays sometimes called the von Klitzing unit. I would think that, in fact, E squared over h entered into these early ideas so thoroughly that the unit really belongs to Mott, if anyone, if not to David Thales or Rolf Landauer. Landauer studied the conductance of a transmitting channel, and I don't want to denigrate the importance of Landauer's work. It's very important in conductivity theory in general, and I'm sure, well, I hope much of your thinking on localization uses the basic Landauer scheme. Thales was the first to introduce the idea of dimensionality. He studied one-dimensional and two-dimensional. Well, it wasn't the first to introduce the idea of dimensionality. Mott had already said, well, and in fact, it seemed to me an obvious remark that one dimension was always localized, and Mott and Borland had already hypothecated that, but it was an obvious corollary of the proof that I gave anyhow. But Thales noted that there would be a critical conductance of the two-dimensional metal, and in fact that had been observed many years before. And the subject began to sort itself out a little bit at the 1978 Laser Summer School, which I think was a very important moment in the revival of the idea of localization. So then we found, well, I'll just add a postscript that what happened really in 1977 and 78 was that we had this group at, there was work going on at the same time by Licciardello and Thales, who introduced this general idea of there being a one-parameter scaling of conductance in units of E squared over h against size. This came more or less from Licciardello and Thales, and Weger in Germany was doing similar things. But Elihu Abrahams and Don Licciardello, who had come to me from David Thales, whose student he was, or a postdoc, I guess he had been, and myself, the idea was suggested by Licciardello and Thales that there might be a one-parameter scaling of conductance versus size of this sort. The second idea that came from L.U. Abrahams and Ramakrishnan, I guess, was the person who first mentioned the use of this old paper of Langer, who had found that cross diagrams diverged in a perturbation series for the Kubo formula. So there was we could find the first correction in 1 over the conductance, from which is the interaction. It came from this old Langer paper, and we developed something called the Gang of 4 paper. It was the appropriate time to refer to a gang of 4, and we were a gang of 4, so it came to be called the Gang of 4 paper. And what we did essentially was to open the floodgates to the use of standard diagrammatic methods for doing conductivity. And so we began the era of weak localization at that time. The paper involved is in PhysRev Letters in December '78. And only one more thing happened that I was involved in, at least. Again, there was this question of really doing careful, good experiment. Doug Osheroff, famous for other reasons, and Jerry Dolan were trying to make thin films into one-dimensional wires to test the predictions that David Thales had been making about one-dimensional conductance. But they made their wires too thick at first. They didn't seem to see David's ideas, but nonetheless, their I versus V curves were never quite straight. And you can trust Doug Osheroff, who is one of the world's marvelous experimentalists, never to take it for granted that any particular line on one of his experiments is straight, that it really was a straight line. It wasn't really a straight line. It was an x log x line. And so he eyeballed it, and he called me in, and I said, oh, that's an x log x line. And we realized that that meant that the resistivity was the logarithm of the distance over which an electron could travel without an inelastic collision, and that this distance was could be shown to be proportional to a temperature to a certain small power, or the temperature in turn was more or less proportional to the voltage that you used, and so you get nonlinear resistivity effects. And so we wrote another paper in which has sometimes been called the Gang of 3 paper, with L.U. Abrahams, Ramakrishnan, and myself. Once this could be done, the field theorists and various experimentalists could play to their heart's content, do all kinds of diagrammatic games and beautiful games with changing such things as spin orbit interaction and magnetic fields, and demonstrate that, sure enough, there was a localization effect. So the thing was done. I'm guilty. Thank you.
Presentation is now open for discussion. Please.
I have a question. You talked about the past or the history of this field. I have a question about future. Uh, as a physicist, I'm interested to know what do you think is the like a challenging open question in the field from the physical point of view, still open.
Well, I think there are many. It's still this problem of interactions and localization acting together is somewhat open, although recently, well, there's a famous experiment in 2 dimensions where it seems certain that the interaction effect is reversing the conclusion of the Gang of 4 paper and showing that there can be a metallic phase in 2 dimensions in spite of our theory. And the Gang of 4 theory, that is. That may have been solved by Panus and Feigenbaum. I think it has been, but it certainly is a challenge to go on with that work and make it more convincing. That's a rather specialized area. There's lots and lots of work in localization of other kinds of waves. That is still an interesting thing to do. Localization keeps cropping up in surprising places. One of my colleagues works at the plasma lab at Princeton claims that there's localization of the excitations in I forget which kinds of waves they were, but he detected localization of the waves in a fusion machine plasma. Another experimental field that's interesting, and has never been really identified as a localization problem, but in fact is something called, what is it? Infrared, Raman, the enormous enhancement of Raman signals by absorbing your molecules on a silver or other surface, a rough surface. That, in fact, is one of the really early games that one could play with localization. You could show that the 4th moment of the density or of the Green's function was anomalously large, showing which the density of states in ordinary localization is not affected, but the fourth moment of the density is very strongly affected by localization, and the Raman effect is proportional to the 4th moment of the density. I don't know that anyone has ever really worked out that sum. The experimentalists have all kinds of particularly very detailed ways of thinking of it, and I'm not saying they're wrong, but I think that the whole thing is subsumed under a localization of surface plasma waves. Well, any good mathematical idea opens all kinds of doors, and there are things that you can do with it.
More comments, questions? If that's not the case, let's wrap it up. I didn't say it at the beginning, so I could say it now without repeating myself. We are truly delighted to have Phil Anderson with us, and particularly delighted to be witness to these reminiscences, his reminiscences on the origins of Anderson localization. Another omission of mine was to welcome all of you, as this probably is the director's prerogative. However, I believe that in the name of David Wallace and the Newton staff, I may now invite you to a reception. So, if you haven't felt welcome up to now, please do and enjoy.